All right. So, for anybody who wasn't here, this is the way it works. You two should pay attention to this part because or were you here when I did Kirchhoff's rules? Okay.
I was here. I wasn't.
You were here. All right. So just Colleen, pay attention. So this is the battery right here. This represents the battery, and the nomenclature or the convention is that the big plate is the positive side and the small plate's the negative side. And because of Ben Franklin, who thought charges moved from positive to negative, he thought that there were these positive charges that moved through circuits. He didn't know about electrons. We say that current goes this way. Doesn't really. It's really electrons going the other way. But we're stuck now because the first textbook said that, and then they didn't want to reprint them, so we just pretend, and we will forever, I guess. So what we do in this is you first take a guess at what the current's going to do, which way the charges are going to flow. If you need to talk, go in the hall. So they get pushed out here, and then they hit this junction, and some of the current's going to flow this way, just like a river, and some of it flows this way, and there are these two little islands here. And then the river comes back together, and then it's the full current again. So this current is equal to those two currents separate. And that's one of Kirchhoff's rules. He's got this thing called the junction rule, which says for any junction, like this junction or this junction, I think I chose this one, the sum of the currents going in, which would just be I1 here, equals the sum of the currents going out, which is what I've called I2 and I3. So that's where I get my equation. And we've got three different currents in here, and we've got to figure them all out. So we need a system of equations with three equations, and that's one of them. So for the other kind of Kirchhoff's rule, it's called the loop rule, and it works like this. Let me just demonstrate with a coffee cup. All right, so coffee cup right here. Does that have potential energy?
Yes.
Yeah, if I let go, then that potential energy could turn into kinetic energy. Okay, so I'm going to change its potential energy a few times, and I want you to tell me what the sum of all those changes is. Okay, I'm done. If I add up all the changes in potential energy, what do I get?
Zero.
Zero, right. So I'm doing some positive changes. I'm increasing the potential energy, increasing it, and then I decrease it below what it started at, and then I increase it again, and I get back to where I was. So all the sum of the changes has to equal zero. That is what's going on in every circuit. If you take a loop. So this point right here, this is like where my coffee cup was in space. And when the charge comes right out of the battery, it's loaded up with 12 volts, which means every coulomb of charge has 12 joules of energy. By the time the charges get to over here on this side, they have 0 volts, which is 0 joules. So they've lost all their energy. So they have energy stored in them, but less and less storage until you get to here. But if I could take some charges and move them this way, and then I go through here and then come back to here again, this part has a certain amount of potential energy. So if I move around and come back to that place, I'm going to have the same amount of potential energy, which means the changes in potential energy, leaving this and coming back to it, have to add up to 0. So that's where this junction rule comes from, or sorry, the loop rule. So I did the loop rule. I made some really clear notes about which way I went and where I started from. So I went through the big loop, and I started from the top left, and I went clockwise. So I start from here. And here's what I do. I go through a resistor. A resistor is something that uses up energy. So it takes voltage. Voltage, you could think of it as the amount of energy in the charge, and voltage equals IR. So if we want to know how much voltage gets taken out here, start with 12. Okay, you two, go in the hall. Go. Come back when you're done. Seriously, go. Go, go, go. No. Max, go. No, go. You had a chance. Go. Come on. Do I need to count to 10? I'm going to count to 10. 1, 2, 3, 4, 5, 6, 7. He'll get a separate count. 8, 9. Okay, Riley, you go. You get 10 seconds too. 1, 2, 3, 4. There'll be consequences if you don't make it. 6, 7, 8. No, I didn't. Just didn't say it. Okay. All right. So, anybody else who needs to talk, go in the hall. So what was I saying? Oh yeah. So the battery loads things up with joules of energy. 12 volts means 12 joules for every charge. And these resistors, they use it up. So we're going to drop it. We're going to lose voltage. And the amount of voltage we use, we can calculate with Ohm's law. I've called this I2. We don't know what the current is. We're going to find it out. So I just use that for my variable. So there's my I2. And this is the resistance, 1 ohm. So since I start from here, the first thing I do is I lose this much voltage. And then I go through this resistor. This is the same current. It hasn't split apart or anything, so it's still I2, but it's 3 ohms. And then I get to this junction, and we assume that the wires don't have any resistance. In reality, they do. And then I pass through the battery from the negative side to the positive side. That adds 12 volts, so plus 12 volts. So I get this equation. Since I'm starting and ending at the same point, the amount of potential energy is going to be like equal in those places, so the change is 0. So when I group the like terms, solve, I get 3 amps for this. That's 3 coulombs per second. And then I could do, how many more loops do I have in this circuit? I did the big one. I've got 2, well, I could do 2 more. There's this one, this little one, and this little one. So I could get 4 equations here. I don't really need 4 equations because I've only got 3 unknowns. So I decided to do the top right loop. You probably could have done the top left loop. So I did this one. And I started from the top left. So I did the same thing. Starting from here, going with the current, I subtract the energy that this resistor takes out. So that's the minus I2 times its resistance. And then I go through the 3 ohm resistor over here, just like I did in the previous thing. So the current is I2, the resistance is 3 ohms. Then I go through here. So now I'm going backward. As the current flows through here, voltage gets used up. So the voltage is going to decrease from here to here. So if I'm traveling this way, I need to add it. So when you're going through resistors with the current, you subtract voltage. When you go through against the current, you add it. So that's why this is I3 times 2 ohms. There's I3 times 2 ohms, but it's plus, it's not minus. So let's see, I've got I3 in here, and something's funny. I wrote something funny here. This says, oh wait, sorry, I'm looking at the wrong line. So I2, I already figured out I2. It was 3 amps. So I'm substituting 3 amps in for I2. That's why I have this here. So 3 amps times I1, 3 amps times, or sorry, 3 amps times 1 ohm, 3 amps times 3 ohms, subtracting all that. And then this is just I3 times 2 ohms. This comes out to basically I3 equaling 6 amps. So I've got I3 is 6 amps, I2 is 3 amps, and if this is 3 amps, and this one is 6 amps, and then they come together, like I2 plus I3 is I1, then I1's got to be 9 amps. Now this little table over here to the side is just something you won't always have to deal with, but sometimes you do. I just want you to find voltage, current, resistance, going through all these things. And it's a little confusing. I feel like I've got to be really careful with this. So we have 3 resistors and then the source. The source is the battery. And the 3 resistors are the 1 ohm resistor, the 2 ohm resistor, and the 3 ohm resistor. So I'll just focus on this line. For the 1 ohm resistor, which is that one right there, the current going through it is 3 amps. It's I2. And voltage equals current times resistance, so 3 times 1 is 3. This is how much voltage the 1 ohm resistor gets. And then the 2 ohm resistor, that's right here. The current is I3, which is 6 amps. And the resistance is 2. 6 times 2 is 12. So this is getting the full 12 volts. And then the other resistor, the 3 ohm resistor right there, current going through it's 3 amps times 3, 9 volts. So now that I know that, I could just say, I pump this up to 12 joules per coulomb. When I go through this one, it's going to lose 3. So now I'm down to 9. When I go through the 3 ohm one, it's going to lose 9. So now I'm down to 0, and I get pumped back up. If I go through this middle gate, I start out with 12, I go through the 2 ohm one, I lose 12, I'm back to 0, I get pumped up again, so it all makes sense. All right, so I spent a lot of time on that one. This one, these, oh, sorry, got my answers to that somewhere else. I started doing that and then decided to switch to another sheet. Here we go. These are all the answers for this one. So if you did this one, the current through here is 2 amps. The current through here is 1 amp. The current down there is also 1 amp. And the chart goes 1628, 414, 414, 1226. Anybody want me to go over any of that? Okay, so now let's do one together. Your homework is to do the very last one. So this one's for homework. We're going to do this one. And it's got 2 batteries. So first step is to guess which way the currents go. So right here, which way do you think the current's going to be flowing? Clockwise or counterclockwise? Clockwise. It's going to get pushed out by this. So it's going to go like this, and it's going to go around here. And how about over here? Which way do you think it's going to go? Clockwise or counterclockwise? Counterclockwise, like this. So it may be. So what might happen is, let's pretend. Let's say the current goes through here, and then it splits, and it goes around like this, and then back in, and then the current through here goes like that. Is that possible? Is it going through these batteries the right way?
Yeah.
Yeah, so maybe it does. If it doesn't, then what we're going to find is one of our currents is going to turn up negative, which means we've drawn it the wrong way. So through here, oh, actually, how many distinct currents are there in this circuit? 3. So there's this one all through here, which I'm going to call I1. So this doesn't get split up at all. It's all one current. And then there's this one through the center here that I'm going to call I2. And then there's this one over here that's I3. And
Why isn't that one just one? Because it goes all the way around.
this one, because let's focus on the junctions. So this is coming into the junction right here. And then coming out of the junction, there's this one and this one.
So isn't that 2?
So there's this one, and this one. So this is one, and this is a separate one. And they're both different from this. This is the full river. And the river, how many islands are there in this river? If it's a river? 2. There's an island here and an island here. So the main river, actually, the way I've drawn this, there's the river coming around here and the river going around there. So it's kind of like 2 rivers that come together right here in the center, if I've done it right. But I may have done it wrong, and we'll figure that out as we go. Okay. Junction rule first or loop rule? I don't care. Which one do you want to do? Which one do you think is the easiest? junction or loop?
Loop.
Loop's harder. Let's do it though. Let's do a loop first, and then we'll treat ourselves to a nice easy junction. So how many loops are there? 3. How many little loops? 2. Do you see the big loop? So a big loop could be this whole thing, and then this is a little loop, and this is a little loop. So which one do we want to do, big or one of the littles? Which one, top one or bottom one? Top. So I'm going to do top loop. And now, which way do we want to go through the top loop? Do we want to go clockwise or counterclockwise? Clockwise. And where do we want to start? Before the battery or after the battery? After, okay. So I'm going to start, I'm going to say from top right. So here we go, starting from here. We go this way, and we're doing the top loop, so we're going through this resistor. Do we add this voltage or subtract? Yeah, voltage equals IR, so it's going to take away I2 times 2 ohms. Mr. Chase or whoever made this left out the ohms on there. So this is minus I2 times 2 ohms. Okay, so keep going. Now we go through this battery. We're going from the negative side to the positive side. Do we add or subtract the 12 volts? Add, plus 12 volts. And then we go up here, and we're going through this. I think I need to plug in my computer. Do we add or subtract this 12 volts? Add. And then we're back to here where we started, which means it all should add up to 0. I'm going to plug in
15 volts.
Oh yeah, 15. So don't write 12 like I did. I'm in such a tizzy to get my computer plugged in before.
Why did we start at the top right corner?
We needed to choose a point. You can pick any point you want. And it was just a point that was easily identifiable. Riley can come in too, as long as you can be quiet. So this should be 15. All right, so we have how many volts total? 27 volts equals I2 times 2 ohms. So what's I2? 13.5. 13.5 watts. Amps. All right, so we figured out I2. Now let's do the easy one. Let's do a junction. Doesn't matter which junction we do. Do you want to do the left one or the right one? There's one here, and there's one there. Let's do the right one. So this junction, what current is going in? Or currents? How many currents are going into this junction? Two. I1 and I3. So I1 plus I3 equals what's going out, which is I2. All right, so there's our junction rule. That's the easiest one. Now we need another loop rule because we've got 3 unknowns and we need 3 equations. So we've got 2 choices. We could do the big loop or we could do the bottom loop. Bottom loop. Okay. Bottom loop. Do you want to go clockwise or counterclockwise? Clockwise. Ooh, boy. Clockwise from where? Either choose bottom left or bottom right, because those are easy points to identify. Bottom left from... Do you see why I said, ooh, boy? Yeah, because we're going against the current, so we're in backward pretend world. We're already in pretend world because of Ben Franklin, but now we're in backward pretend world.
So wouldn't that just be real world?
I don't know. No, it's backward because we're going to be, maybe so.
Can we go counterclockwise?
No, we're going clockwise. Decision's been made. So we're starting from here, from right here. We're swimming upstream. We go through this battery backward. We minus 12. So minus 12 volts. And then we go through the resistor backward. Do we lose energy or gain energy?
Yes.
We gain energy. So it's going to be current times resistance. So it's 2I2, or I2 times 2 ohms. And then we go through here, again, we're going against the current through this resistor, so do we add or subtract? Add, we're adding voltage, because there should be more voltage on the upstream side. And it's going to be the current, which is I3 times 50 ohms. And then we're back to where we started, so it should all add up to 0. All right. What can we do? We've got two variables in this. Yeah, we can substitute this in. So, and I'm going to move this to the other side. So instead of I2, I'm going to write 13.5 amps times 2 ohms plus I3, which we don't know, times 50 ohms equals 12 volts. And this would be 27 volts plus I3 times 50 ohms equals 12 volts. So I3 times 50 ohms equals what? How many volts? Negative 15 volts. So I3 equals negative 15 over, yeah, negative 0.3 amps. Okay, so the fact that this is negative 0.3 amps means what about this? Yeah, I3 is really the other way. So I3 is 0.3 amps leftward. So that's actually the direction of the current. And then I2 is drawn fine. This is 13.5 amps. And what's I1? Yeah, it's the two added together. So 0.3 plus 13.5 is 13.8 amps. And that's it. So that was good. I'm glad you wanted to go clockwise so we could have a negative current and deal with it. Well, no, that wasn't really what that was just us drawing it the wrong way. That's what gave us a negative current. Going clockwise wouldn't have mattered. We wouldn't have got a negative answer if we had gone counterclockwise. It would have been just fine if we had drawn this correctly in the beginning. So your homework is to do this one. But we've got a little bit more to do in class before then, so don't get started on it quite yet.